Um, actually, let me have your quizzes, and then I'm gonna just kind of work through the whole thing. And it should illuminate some of those formulas you saw, and formulas you used. And this course should not be taught using those formulas, but it is needing to know where the formulas come from, so that you understand exponential functions rather than just know how to punch maybe a calculator. So, okay, so our goal is to understand exponential functions. Your formula, your book gives you a perfectly good formula that you give an eighth grader. That's not a pre-calculus level exercise unless you do certain things with the formula. And some of those things do get done, so it's not totally bad, but it's ridiculous in the first place if people come out of high school where they have a finance course required in this state and don't know what compound interest is. I knew what compound interest is when I was 11 years old. I understood it, and so did most of my friends. Okay? You start, I mean, when, my parents set me up with an account with, like 50 cents in it or something, I don't know. But, you start putting a little money into the account and you start wondering what's happening with it. If you understand percents, which you do at 11 years old if you're in any kind of an educational system. Okay, so anyhow, it's 6% annual interest compounded monthly. Okay, well, what's the monthly rate? So first of all, we don't want to deal with the percent signs. We're going to change the percent to 0.06, and I think everybody knows that. Okay, so 6% annually is 0.06. Yeah, I think most of you got this. And I wrote 6% monthly, which is totally wrong. Really having a rash of writing down things that I see rather than what I know. Okay. Monthly rate, which is what I called it, which is what everybody, just about everybody calculated, 0.005. Look at that decimal closer. Okay, so monthly multiplier, you don't know what that means. Maybe you didn't have a problem with that terminology in it. So let's just skip to what the interest is for the first month on $1,000. Okay. Interest of $1,000. If the monthly rate is 0.005 times $1,000 equals $5. Okay. Now, what's the interest in the second month after you get this interest in the first month? That word is after. 0.005 times the amount after the first month. What's the amount after the first month? don't say it, but yeah, it's $1,005. Okay, because you had interest of $5. Okay. We could calculate that. It's not difficult to calculate, even if you don't use a calculator, but I want to do it in my head because I'll mess up my zeros or something. Simple binomial expansion though. Okay, so $1,000 plus $5. Well, we're going to note that $1,000 plus $5 you have at the end of the first month is 1.005 times $1,000. Okay. As a matter of fact, I'm going to write that a little differently. I'm going to write that as 1 plus 0.005 times $1,000. So we can really see what this is saying. It's saying that we multiplied the $1,000 by 0.005, that gave us $5, right? And then we multiplied it by 1, that gave us $1,000. Okay, distributive law then is 1 times 1,000 plus 0.05 times 1,000, which is $1,000 plus $5. Okay. I'm having a hard time with chalk today. I don't know why that is. Okay. Make sense? Okay. Now I'm skipping a little bit, but after the second month, I claim that we're going to have 1.005 times 1.005 times $1,000. Now, what's this mean? 1.005 times $1,000 is what we have after 1 month, right? Well, if we do another month and add 5% to what we have, it's the same as multiplying by 1.005, right? You saw here, multiplying $1,000 by 1.005 was the same as adding $1,000 to 0.005 times $1,000, right? So you want to convince yourself of that, but I can start filling things in. The monthly rate here, 0.005, the multiplier, the thing we would multiply by to add 5% is 1.005. I multiply by 1 plus 0.005, I get my money plus 5%, right? Same as multiplying by 1.005. So this is how you add 5%, or 0.0, it's half a percent, it's 0.5%. This is how you add 0.005 of your money, right? Your monthly rate. So that's a multiplier. There's another word that I like even better. I call this the growth rate and the growth factor. Okay. And I'm going to give you those words, and I'll probably be using them, but I'll explain. This is the growth rate. I'll put, better put the word monthly in there. This is a monthly growth rate. This is the monthly. Growth factor. Okay. Understand why this is a rate, because you're used to talking about a percent as a rate. At least I hope you are. If not, get used to it. Okay. This is a growth factor. A factor is something that's multiplied by other things. So you multiply this growth factor by whatever amount of money or whatever population, if you're doing population dynamics, or whatever it is that's growing, okay? You multiply the growth factor by how much you have, and that's how much you're going to have after the period. In this case, a period is a month. So, okay, so we haven't totally answered these questions, but the answers are implicit in everything we've done. We did answer the interest for the first month, just 0.05 times your $1,000, right? Interest for the second month, well, we would take 5% of that. $1,000, $1,005, right? I wrote it as $1,000 plus $5 because I was going to do this. But we multiply by the new amount. Now, people will think in terms of simple interest. If it was simple interest, it's 6%. You'd just be getting 5% of your $1,000 every month. You wouldn't get 5% of your $1,005. You just keep adding $5 every month. You get $60 for the year. And then you get another $60 from the next year. And your money wouldn't be growing based on how much you have. It's growing based on your initial amount, which is less. It's simple interest. I don't know of any place where people really do simple interest unless they're dealing with very illiterate people and probably defrauding them. Okay. There might be cases. I don't know everything there is to know. Actually, I do, but I try to be modest. Okay. Yeah. You agree. All right. Okay, so my question is, what's the value after 8 years? Well, writing that kind of small, but it says multiply by 1.005 each month. Okay. Now let's see how that works. Let's go back to this. After the second month, you agree. After the first month, we had 1.005 times $1,000. And after the second month, we have 1.005 times that, right? Of course, that equals 1.005 squared. Times $1,000. Can you see that square? It's kind of messed up by that parenthesis there. Let's see if we can make a big smudge and make it even worse. Okay. You can get 1,005 and 1,005. How many times are you going to multiply by 1,005 in 8 years, or about 1.005 in 8 years? Well, you're going to multiply 8 by 12, right? You got 12 months in a year, 8 years, 96. Good. Very good. Okay. I'm going to use P for the principal. Okay. P of 8 then equals $1,000 multiplied by 1.005 to the 96th power. And that comes out more than $1,610 and some cents, I think. Okay. That's pretty easy to do. Now, let's talk about that formula. Better yet, let's derive the formula. We call initial principal P sub 0. That's a subscript, just indicates that that's what we have when we start at time 0. Okay. It's RB, your annual rate. Okay. Compound monthly. So your monthly rate you divide your annual rate by 12. Most of you did that spontaneously. Didn't have to explain anything to you. Some of you missed it, but you understand. Okay. Some of you didn't think that way because I think in most cases you're trying to think in terms of that formula, which you remember nicely. So, you know, that's good. But okay, there's our monthly rate, R over 12, right? So the monthly multiplier, which I'll call the monthly growth factor, is 1 plus your monthly growth rate. That corresponds to 1.005 in our example. Okay. Apply the monthly growth rate 12t times in t years. Does that make sense? Because there are 12t months in t years. If you know the number of years, you multiply by 12 to get the number of months. I probably didn't even have to say that last thing, but just to be sure. Okay. It's 1 plus R over 12 raised to the 12t. Does that start looking like the formula you used? there's a reason for it, there's a meaning behind it that I don't think our materials explain. I could be wrong. I need to look at the text to see if I'm telling the truth or not. Okay. Actually, I think they do some explanation. I'm not sure if the videos do. Just give you the formula and tell you to use it. I do not agree if that is the actual approach that they're taking. And I like open math pretty well. Okay. So I'm not being too critical of it, but I am critical of the idea that in a pre-calculus course, you give people that formula and don't require that they understand it. There are people who would disagree, knowledgeable people who are otherwise pretty smart, but they're stupid about this. Now, seriously, I respect other opinions. And a good case can be made. Okay. So that's a growth factor of 2 years. So how do you get the amount of T, your principal after 2 years? You start with your initial amount and multiply it by your growth factor. Your 2 year growth factor, okay? Which is this. Okay, now. Compound n times annually. The rate per period is R divided by n. Number of periods in 2 years is nt. It's exactly like this, except we're using n where we're using 12 here. So if you're compounding it daily, now actually when they compound daily, usually they compound 360 times a year. It's regarded as daily. You don't want to try to do 365.24 compoundings in a year. 360 is a nice number, okay? It's an easier number to think of. So it's not quite daily, but it doesn't make much difference. So n would be 360. The period would be 1 day. So every day you would add R over 360. If R is 6%, okay, 6 over 360 is like 1 over 60, like 0.0016 repeating. Yeah. Okay. It'd be different than what we got there. It'd be different than a 0.005. Okay. I think I need one more zero on that one I just mentioned, but it's easy to calculate. It's easy to put into a computer. You put 360 million in for the number in your Excel spreadsheet, and then drag it down 7 billion times, and look at what you have. Okay. I think you want to drag it down that far, and I don't think Excel would handle that, but okay. Hey, there are other things you can do with Excel. You put this into Excel pretty easily. You put it into an actual computer, easier than that, because you just really come down to this formula. But the formula in this case is every period, every day, let's say you have this much, or you multiply by this much to get your new amount. And then you multiply that amount by this much for the next day and so forth. And you do that for n equals 360 days every year. So in 2 years, you do 360 times t, right? And n could be any number. Okay. Now, okay, we approach continuous compounding where P of t equals P naught e to the RT, which is much simpler than this. And it gives you more money. Okay. Because you're compounding every instant. Another thing I started thinking about when I was 11 or 12 years old was continuous compounding. If you think about it, it means you compound more and more times, less and less percent each time, but it keeps growing. Okay. I was a little more mathematically adept than most 12-year-olds, so I could think about that a little better. But I had at least 3 friends who were smarter than I was. Okay, and that helped. One was a lot smarter. He's also a sub 420 miler. Smartest guy in the county. It was a big county. Population of all Southwest Virginia in one county. His dad was my doctor. We knew him. Okay. Worked with him 2 years in the metallurgical lab in a steel mill. Doing grunt work. It was okay. He was at the top. Okay. Another one of those friends was one of 2 representatives from the state to the national spelling bee. Okay. And another one was a daughter of my parents' second best friends. Okay. I also had friends that got held back grades and stuff like that. You know, you get them mixed. The point I'm making of that is just one other example. Another buddy, he's a good student, you know, reasonably smart guy. But we played a lot of football because that's the sport in my town. You know, after school we'd be on the football. You know, we weren't on the team because we didn't like that much organization. But some of us were pretty good. Like this guy could throw a football. I'd take off. We had 40-yard lots. He'd be at the boundary of one 40-yard lot. I'd take off, run past the boundary of the first 40-yard lot and keep running. He'd throw the ball and I'd catch it just shy of the next 40-yard lot. Measured at least, and you know, judging from where I caught the ball and where it would have landed if I hadn't caught it, darn close to 80 yards. Okay. Now scrawny little me and throwing the football back and forth with him, that eventually developed a 55-yard arm, which is a pretty good arm. Okay. It's not elite. Not going to get you into the pros, and if I'd have been accurate and halfway athletic, I might have been a pretty good quarterback. If I had the patience to learn playbook. I had mathematics and engineering to learn. Okay, all that's a digression, so we can talk about this a little bit, okay? I'm just talking about, you know, you tend to come up to the level of what you're around, or come down to the level of what you're around. That's my main point. Okay. There's our formula. And the reason for this formula is that E equals the limit as n approaches infinity, n being the number of times you compound, if you wish to talk about that. If the number of times you compound in a year approaches infinity, that means the period approaches zero, right? And you got this limit thing, and it's the limit of 1 plus 1 over n raised to the nth power, which looks kind of a lot like this or this. You're just leaving the r out in the t. Okay. I think it's important for a pre-calculus student to see that, and I think it's important for a pre-calculus student to do even a little more than that. Like evaluate this for n equals 1,000 or 1,000,000, just punch it into your calculator. And that's approximately 2.71828, and it just keeps going. And the numbers don't repeat, even though it looks like they do, because just 1 in a 2,000 chance, you get another 1828 before the numbers start changing. There's no pattern. You calculate it then in number significant figures. Okay. A little more detail that I went over. I did the same problem in the MDE class, but we developed it a lot more slowly. So you can see how it was developed here. This pretty much mimics what I said here, but it's a little more compact. I said it a little more compactly in class here. And then we talked about continuous interest at 6% here. We worked out some details. But down here, we actually did some calculations. If you want to see what we did in that class, you look at the video. But right here's something should be familiar to you. That's the formula we just derived, okay? I'm not sure we even did it. I guess we didn't. Anyhow, okay. We compare what you get with this formula, which just comes down to this, okay? And the 12 T's up here, that we calculated 1.005 to the 12. 1.005 to the 12 T is the same as 1.005 to the 12th raised to the T power. That's just your law of exponents. A power of a power, you multiply powers, okay? And we got 1.0616. Now, if we were compounding once a year, we would have annual compounding. So I'm going to contrast that. You would have P of t equals P naught times 1.06 to the t. Doing monthly compounding, instead of 1.06 to the t, we have 1.005 to the 12th raised to the t. And 1.05 to the 12th is 1.0616, meaning our effective interest rate is 6.16%. Okay? If you did continuous compounding, it would be e to the 0.06. You plug that into your calculator, it's going to be a little bigger than the 616, maybe 6.2 something. Okay? It's interesting to do. Now, the thing I want to, one thing is the comparison. You get more interest, which means your money grows faster. And over 8 years, if you invest $100,000, it turns out you get about 500 extra dollars by compounding 12 times. And probably another 300, 200 if you compounded it continuously. Okay. This is an exponential function. It's of the form a, b to the x, except for using t instead of x. So this is exactly what you've been working on when you did your exponential functions, okay? Where b is what's raised to the t, that's your 1 plus r, or 1 plus r raised to the nth power, whatever it is, okay? A is your initial interest, and there you have it. So this is just an exponential function. This is a pretty simple exponential function. That's pretty recognizable. You just got a number times a base raised to the power, okay? All right. So it's worth understanding the details of that, which is what I just took approximately 15 minutes of your life to enlighten you. Hopefully, there's a little enlightenment there. Hopefully you'll think about this a little more because it really is relevant to financial planning and stuff. Okay. There are formulas, but you can understand the formulas a lot better than some accountants. Now, the accountant that did my taxes for this year, well, my wife's my taxes this year, because we don't want to mess with that. Yes. They always find ways to save extra money legally, and they're worth what you pay them. The guy's an engineering student at Tech. Got tired of engineering, went into accounting. So I think he understands these formulas real well. The accountant that used to do them is a former student who did well in calculus. And I think he understands it. I'm friends with another accountant, and I don't really try to penetrate what he knows, but he's a darn good accountant. Okay. And I suspect he understands it. And sometimes accountants just throw things into the computer and use formulas that they don't understand. They still get it right if they're meticulous. Okay, so I'm not sure it's necessary for an accountant to understand the formulas, but I think it's a good idea. I think it's a good idea that anybody that deals with money, which everybody has to do, should understand the principles in the development of this stuff. All right. I'm going to come back to where I was here, and I'm going to take off from this point. Next assignment deals with logarithms. Now, a logarithm is just the inverse of an exponential function. Logarithmic function is the inverse of an exponential function. Okay. How do you do inverses? You swap. Okay. You reverse your variables. Okay. So I did that here. You should understand what I've done. These vertical lines are x equals -1, x equals 1, x equals 2. Okay. I've got y equals 2 to the x in white here. And I've got y equals 1, 2, 3, and 4 up here. It's not particularly well drawn, not particularly accurate. My spacing's a little weird. I wasn't real careful about it. If I wanted good equal spacing, I'd have started with 4, divided that in half, divided that in half, now stuck 3 in the middle of it. Okay. But I did 1, then I did 2, then I did 3, then I did 4. It doesn't work as well as what I've had you do when you construct these things. Okay, but I didn't construct it in a rectangle the way we've done. Because I'm just using basically x equals -1, 0, 1, and 2. So I've got a table here, and I've got graphed the points of the table. I graphed them before I made the table, because you know what's going on with 2 to the x. That's a function you understand quite well. Okay, but there's the table for 2 to the x. And here's the table where I put the numbers in the y column and the x column. We swap x and y. Okay, and you can see that I've done that. The -1 through 2 goes there, and that 1/2 through 4 is here in the second column. It goes into the first column. Okay, and I plot those points right there. They are in white. The name of that function is the log base 2 of x. Y equals log base. It's a log base 2 function, inverse to the 2 to the x function. Okay. I also did a representation. It's not very accurate, but the 3 to the x graph. It's not that far off. It looks about like that. So that compares with the 2 to the x graph. Okay. Now I just told you that E was about 2.7. Okay. And then you got a couple repeating 1/8, 2/8, and then you got a bunch of stuff, no pattern. Okay. So about 2.7 means that E to the x in orange here, or whatever the heck that color is, lies between the 2 to the x and the 3 to the x graph, somewhere in there, probably closer to the 3 to the x graph. Probably should be a little closer to 3 to the x graph than I made it, but that's okay. All right, you get the idea. And you can graph it, using computer software, online Desmos, whatever. Okay, if you want to graph it accurately. So a white graph is what we get when we reverse the coordinates of this white graph. And that's your log base 2 of x, 2 to the x, log base 2 to the x, log base 2 of x. Okay. And then in this color, whatever it is, we got y equals e to the x and y equals log base e of x. Okay. Log base e of x is also called the natural log of x, because e to the x is the most natural function in the universe. And this is the most natural logarithmic function in the universe. And if you study theory of complex variables for just a little while, you understand, and you don't even have to. You can do it in second semester calculus, much less advanced undergraduate work. Okay. You see that the e to the x function can be used to define sines and cosines, which have graphs that do this, and where the e to the x graph does this. Don't ask why, don't ask how. You want to remain sane. Okay. Because that one will drive you absolutely nuts if you let it. Unless you have a fairly powerful mathematical background, okay? Even then, back in the days before computer visualizations and stuff, it drove a lot of us happily nuts trying to visualize it. Okay, a little easier to visualize now. You can see it, you can understand it. A second semester calculus student can understand it. Visualize how that doing. All right, so what we really want to talk about is what good logarithms are. Okay, you got these logarithmic functions. This is how they're graphed. This is how they are defined. The way they're used primarily in this course, there are a couple of ways. They're logarithmic models, but one of the main uses is to solve exponential equations. Let's say you wanted to solve I'll just use a simple function that we have to get. Invest $1,000 at 6%. The solution to this equation tells you at what time, how much time has to pass before you have $8,000. Now, that's going to be most of a lifetime. But I've lived long enough to see it. Even if I started at the age of 60. Oh, not that long. Okay. P of t equals $8,000. I can tell you that this will double in about 12 years. So if you start with $1,000, you're going to have $2,000 in about 12 years. And you're going to double that in another 12 years. You'll have $4,000. And when you double that, you'll have $8,000. And that'll be after 3 12-year periods. Okay. Now, relating that to what you know, okay, you know what that is. It's your basic exponential shape. We can label this any way we want. So I'm going to just say that, okay, this is y equals 1,000. And this line is t equals 0. Okay. Now, if this thing doubles in 12 years, then what's t equal to here? Might be able to show me some figures. Well, y is 1,000 here, right? What is it on this line? 2,000. Because the way this was constructed is this line's halfway between here and here, this line's halfway between here and here, and so forth. This line is halfway between here and here, which means if this is, of course, 0, then I guess I should label that. That's implicit in the way this is drawn, but not really. So y equals 0 here. So y equals 0 here, it's 1,000 here. And this line is halfway between this line and this line, so this line must be 2,000, right? In other words, these lines are all doublings. So we can label the y's. Now, how long did I say it takes to double at 6%? About 12 years. So if t equals 0 here, and if the thing is doubled by the time you get here, t had better be 12, right? Right there's a picture of how $1,000 would grow at approximately 6% annual interest. Well, that should be sort of a revelation. Fine. Okay. Well, let's see how we can solve this and see what this picture tells us in the rule of 72, which is a doubling time is about 72 divided by your percent. Okay, 72 divided by 6 is 12. So I got the 12 years. Okay, it's not totally accurate. We're going to find accurately when you're going to have $8,000. Well, solve P of t equals $8,000 means a 1,000 times 1.06 to the t equals 8,000. Make sense? What's the first thing you're going to do with this equation? Okay, I won't mention any names. We had a couple of suggestions. And they were, I can understand the suggestions, but they both violated in different ways the order of operations. Okay, somebody said, well, can you multiply the 1,000 by the 1.06? And my answer was more polite. I'll give it the other end. Heck no, 1.06 is raised to t. You can't multiply before you do the exponent. Okay, so heck no. And then another one was subtract 1,000 from both sides. Doggone it, no. I'm sorry. Okay. 1,000 is multiplied by something. You cannot do a subtraction before you do the multiplication, but you can do a division before you do multiplication. So So 1,000 goes into 1,000, it leaves you with 1.06 to the t equals 8. Isn't that a lot nicer? Now you just have to figure out what power of 1.06 gives you 8. Well, I have ways that I could estimate that. You probably don't. And even my ways aren't going to get me that close, except by shortcuts like the rule of 72. Okay? Binomial expansion, not going to be pretty. Okay? That number is just too big. Now, actually, I could do a little more with it, but I'm not going to. Okay. It turns out that then t equals log base 1.06 of 8. It's not magic, that's just inverse functions. I'm not going to ask you to understand exactly how the inverse function gets you from here to here, but I'm going to give you an equivalence. Okay? So here's the equivalence. If b to the a equals c, the arrow going this way tells you that a equals log base b of c. And the arrow goes the other way too. If this is true, then this is true. Now look at 1.06 to the t equals 8. Okay, you're looking at that? 1.06 to the t equals 8. Is that like one of these expressions? It's like b to the a equals c, where b is 1.06, a is t, and 8 is your c. Okay? So I can rewrite that. A, which is t, your exponent, t equals log base b, b is your base 1.06, there it is, and c is 8. Okay? Now you need one more thing to solve this, and then you have something you put in your calculator. Okay? The other thing you solve is that, okay, what do we mean by log base b c? Well, that equals natural log of c over natural log of b, or log of c over log of b. You have an log button on your calculator. You have an ln button on your calculator. You can use either. The ratio is the same either way. So whichever button you find first, whichever one you'd like to look at more, you can do it. Okay? The log stands for base 10 log. If it's an log base 10, we don't even write the 10. But sometimes we do, just to be careful, just to be sure. And sometimes log means ln. So you got to be careful of who you're talking to. But in solving an equation like this, it doesn't make a bit of difference. Any log will give you, if you use the same log in the numerator and in the denominator, it's going to work. Okay? If you use log base 47, up here in log base 47 down here, you're going to get the same answer you would for ln or for log. Okay? Well, so that equals log of 8 over log of 1.06. I think most of you have calculators. Use them. That could be ln if you prefer to use ln, or if you want to use log, that's fine. Okay, now your calculator probably even has a log base. I don't want you to use that. I want you to understand the proportionality here. I want you to be aware of it, at least for a while. Okay, so don't punch in log base 1.06 of 8. That didn't used to be available. But you don't want people to have to think or know anything, so they put one on there. Okay. And you get 35, was it 35.7? 35.6? Okay, so when I said 36, well, I was pretty close. Okay, that's the rule of 72. I think you're going to see that in open math. And again, it just says divide 72 by your interest rate. That tells you how long it takes to double. All right, so you get the general idea of how we can use logs. Well, logs have lots of properties that are pretty easy to use. And I haven't gone over those properties because I think your text and open math will give them to you, but I'll go over kind of quickly. And we're not going to try to explain these properties, but we can see them in terms of properties of exponents. Okay, like it doesn't matter what base the log is, whatever log, whatever base. I could say log base B on each of these and it'd be valid, but for time, I'm not going to write the B. Okay. Log of A times B is log of A times log of B. Log of A raised to the B power is B times the log of A. They usually give you this one. I always thought this one was ridiculous. Because it just follows from the first two. However, there it is. Log of 1 equals 0. And to explain that one just real quickly, in terms of a picture, you notice that every log function goes through the point 0, 1. every exponential function, any base to the x is going to go through the point 0, 1, because when x is 0, whatever that base is raised to the 0 power, and that gives you 1. Okay? So that point has to be on every exponential function, every beat of the x function. Okay? So that this point has to be on every log function. When x equals 1, y equals 0. Here, when x equals 0, y equals 1 on the log. When x equals 1, y equals 0. And you need to apply these. We are out of time, so I'm not going to hold you any longer. But I think you're going to find the application of these rules pretty straightforward. Now, there are non-straightforward things, and there'll probably be a couple of problems that maybe you stumble over. I'll take a good look before you come in next time, and we'll talk more about them. But go ahead and, read examples, work examples. I don't think you're going to have much trouble with them. And if you do have trouble with some of them, we'll talk about it. Okay. Incidentally, your tests, I've just now this morning picked up all the tests. There are a couple of people that had taken a little bit late for good reasons. Some people really had to take them on a Saturday, and they were installing doors and closed the building on Saturday, and they weren't able to do that. And a couple of health issues. But I think there were 3 tests that got late. So now, in various courses, not just this one. I think only one person in this course. Anyhow, now that I've got all the tests, I'm going to grade them, and I'll post the grades. And that should be before Thursday. Should be. Who knows what's going to come out of the woodwork at me, but if things go according to plan, which they sometimes do, that'll get done. It's a priority.